many of you are maybe familiar with semiconductor devices or like have heard of a diode before? Quick raise of hands. Okay, great, so pretty much all of you. Okay, that's perfect. So that means we don't have to cover all like the boring semiconductor physics stuff. I mean, it's not boring, I like it, but it's not fun. So I'm just gonna give you a quick overview behind diodes, and then we're gonna transition into BJTs, how we use them, and the motivation for them. Then we're gonna talk about how we use them in amplifier circuits, and then we're gonna talk a bit more about different types of BJT structures that we employ and what their purpose is, and then that'll be the end, and then next we're gonna pick up with oscillators. So first, the diode, since you've all have heard of this before, the main thing I would like to highlight about a diode is its rectifying behavior, and by this I mean that you can apply a positive voltage in one direction, and you're gonna have a current as a result. If you apply the opposite voltage with the opposite polarity, no current. So this is what we refer to as rectifying behavior, and it's something we're going to see later on, maybe around lecture 3 in the hardware when we make our mixers. But this guy is very important because this is a p-n junction. And for those of you who have done semiconductor courses, you'll see that this comes up a lot. And even the structure of a BJT is based off of these p-n junctions. So first, we need to have a good understanding of this before we can transition to BJTs. So first things first, we apply a certain voltage, we get a certain current. We need to know the relationship between these two before we can actually use a device. When we use devices, we want to understand exactly how they work, or at least a good approximation, before we can use them. So from your semiconductor physics courses, you'll see that you take what we call a p-doped semiconductor and an n-doped semiconductor. This just refers to, for example, let's say you have a bare piece of silicon. Okay, you're going to now take the silicon and you're going to inject either holes or electrons. And you do this with different types of methods that are covered in your semiconductor courses. But after you inject it, what happens is you'll have your silicon atoms, and they're in this lattice. And I'm going to try and draw this big enough for all of you to see. So these are your silicon atoms. These are your ions. Next thing we do is we want to dope them. So by default, silicon is in the group 4 in the periodic table. So they have 4 electrons already for each ion. Does that make sense so far? Okay. So each one has 4. Perfectly balanced intrinsic silicon semiconductor. Now, if we want to dope this with electrons, we want to make it an n-type. What we do is we add, well, another electron. So now there's 5 electrons versus 4. So now it's overall more negative, hence the n-type. Now, if we want to make it p-type, instead of adding an electron, well, take one away. So now there's 3. And we do this for several different reasons. The main thing is we want to have 2 very electrically different materials. And the reason why, we'll explore in the p-n junction. So this makes sense how we have bare silicon. We can change the number of electrons by either taking one away or adding one, and then we can get either a p-type silicon or an n-type. Any questions? Okay, cool. So moving on to this. We now have these 2 pieces of silicon. This has more holes, and holes, for those of you who don't know, are an absence of an electron. This is something that people have a hard time wrapping their heads around. Even professors don't. Sometimes they give very different explanations. Think of a hole as just a positive electron. It's an electron with just a positive charge. That's it. Just opposite. Okay? So if you understand what an electron is, hole, just the opposite. Okay? Very simple way of looking at it. So what happens here is we are going to take p-n and n and kind of combine them. So what happens is initially they're in equilibrium. You have a certain number of holes, certain number of electrons, they don't interact. You bring them even closer together. Okay, so this is the barrier here. We bring them even closer together. And what we have here, we have ions that are going to show up here. These ions are these things here. Okay? So these charges, they're sitting here. They can't move. They're part of the crystal. What happens is as we bring these 2 pieces semiconductor closer together, these free particles, these holes and electrons that are free to move around, we refer to these as charge carriers, they're going to move away from this plane of contact. So what happens is we're now left with these ions. And what these ions do is they set up an electric field, which in turn creates a voltage across this region, and refer to this region as the depletion region. The reason for this is we no longer have free charge that can move around. Any, let's say, electrons that are over here that will drift into this region get pushed across. Okay? Does that make sense so far? Can all of you see that? Somewhat? Yeah? Okay, cool. So this sets up our depletion region. Now, let's say we apply a voltage now to this. Ideally, well, I'll backtrack. If we have, this is our N type, so P. So electrons over here will go into this region, get pushed across, right? This is a normal electric field, electric field, it's opposite, so, yeah. The electrons here are just going to get sucked this way and then holes are going to go this way, sorry. This is a hole, it's going to get pushed across, and electrons here enter here and get pushed this way, okay? So what we see is that minority carriers in our p-type get pushed across over here. Minority carriers in our n-type, our holes, get pushed across. This is very useful because we now have a way of separating charge based on what voltage we apply. Now, as for how this region changes with voltage is next one we're going to explore. So we have two states for a diode, forward biased and reverse biased. What this refers to is forward bias is when we have current, reverse bias, no current. It's the naming convention. So the way you can think about this now is forward bias is typically we have V greater than 0. This voltage here from the P terminal to the N terminal. Reverse bias is less than 0. So what happens here is as we apply more and more voltage, right, we know that our electric field is proportional to our voltage, right? But how does this happen? There's a certain length of this depletion region that our voltage drops across. So what happens is, as we apply more voltage, this is going to shrink, and our electric field will get stronger. Does that kind of track? It's from our general physics, right? So as we apply more and more voltage here, this region shrinks. The electric field gets stronger. We have a stronger flow now. Because our electric field is stronger, our carriers can get pushed even harder, our current is going to increase. General first order idea behind it. That kind of makes sense? Similarly, in reverse bias, this will extend, and we have less electric field, which means carriers are not being pushed as hard as from this side to that side, current goes down, okay? So there's several different diode models, and I'm gonna draw these out here real quick. There's something called the ideal model, which is this blue curve here. It's going to be 0 up until a certain voltage here, V5. And then all of a sudden, current spikes up, okay? So this kind of refers to the rectifying behavior, as I said before. We apply a certain voltage, a lot of current. If we don't meet that point, no current. It's like a switch. But this is, not how it actually is in real life. We wish it was, but it's not. In reality, we had an exponential dependence, kind of something like this, where our diode current follows this formula. Okay, so kind of confused so far. The main takeaway you should have is that all of the physics, this amounts to this red curve here. There's an exponential dependence in voltage and current. It follows this formula here. So exponential is e to the power of v over vt. And vt is a very small number. It's around 26 millivolts at room temperature. So if we apply 26 millivolts as our voltage, we're going to get a current that's around the value E, 2.714, something like that, right? Because we have e to the power of vt over vt, e to the power of 1, right? So you can see it grows very quickly. And this is something that we want to exploit. This is a characteristic that we'll see very often with semiconductor devices where we have an exponential dependence with relation to temperature as well. So, going from this, we also want to, well, I'll bring it up. Okay, this makes sense to everyone so far. Yes?
Shouldn't there be an I naught in front of the exponential?
Oh, like the IS? Yes.
The saturation?
Yes. Yeah. So that's a very small number. It's around 10 to negative 15. I just kept it as like a 0. But super small number. And we'll see, draw this here. It's super tiny, and you don't even really notice it until you get to high enough voltage. But yeah. Thanks, Harry. Francisco, you had a question? No? Okay, cool. Alright, so that's that. Next thing I'm going to talk about is a BJT. So I'm going to move over here, and everyone here can still see this board, right? It's fine in the back? Yeah? Cool. Okay, so before we dive into a BJT, let's first talk about the need for a transistor. So far throughout maybe your circuit courses, you've seen, resistors, capacitors, inductors, but these are what we call like passive elements, which means we don't get any gain from them. We always see loss going through them, whether it's via voltage or current loss. We don't have a gain of power, and that's something we want to find. We want something that can give us power gain. So, what do we do? So, first order, a transistor is simply a transresistor. What this means is think of a resistor, okay? And we want to modify this voltage here, okay? So as we change some voltage that's tied to our transistor, we're going to change its resistance, okay? So let's say we increase this voltage, okay? We want this resistance to go up or down. We want this to be the only way we can change this resistance. As you modify this resistance can go up or down. The current going across, through it, will go up and down. The voltage across it will go up and down. Does that kind of follow? So a transistor is just some device that we can reach in, tweak one knob, and get different levels of voltage across it and current through it. Does that make sense? It's the first, conceptual look at a transistor. Okay. So, next we have something called a bipolar junction transistor, and I want to briefly talk about different methods of transport. Okay. So in a p-n junction, I briefly brought up that we have an electric field. This is what does all the movement of charge, more or less. We have diffusion as well, but this is the main source of charge movement in a p-n junction. It's the electric field. It's the electric field that we created when we apply certain voltage across it, okay? In a BJT, the main source of movement is not an electric field, it's diffusion. This is important because if we have, I'll use a very common analogy where if we spray cologne over here, it takes a certain amount of time for it to spread across the whole room. And eventually, at steady state, all the particles will be evenly distributed throughout the room, and well, hopefully some of you can there smell it. That's diffusion. One thing to note, which is kind of important, is in a p-n junction, this electric field is going to move poles this way, right? That comes this way. They're going to move in the same direction of your current flow. So if I have a hole going this way, this means I have an electric field going this way, right? This electric field is going to push my hole away. It's going to pull my electron, right? But an electron going this way is positive current going that way. So in a way, these two currents add up, right? This makes sense, right? Everyone got that? Okay. In a BJT, if we have let's say, in a diffusive model, right, we have a bunch of electrons here. They're going to move kind of this way, right? They're going to spread out this profile, okay? But electrons and holes will not always diffuse in opposite directions. My holes can also move this way. If my holes move this way, my electrons move this way, their currents are not going to add up anymore. Versus in the electric field, their currents do add up. So this is something the BJT employs, this kind of subtracting of the two currents based on their concentrations, okay? So what is a BJT? The primary BJT we use are called NPNs, and this refers to, well, they're doping in these three areas. We have a region called the collector. Good. So this is the collector. Something called the emitter. And then we have the base. Okay? So we have three terminals here. 1, 2, 3. 3 currents. 3 regions of the BJT. Now, if you look kind of carefully, see this is a p-n junction, right? This kind of acts in a way, same diode over there. Same for this. Right? Good so far? So what happens here is that we want, generally speaking, to be able to tweak this area here and to get a resulting change over here in the current. Because what's happening is we want current to primarily go from here to here. This is our main output. So ideally, we want to modify the voltage here and get a change in current. So what happens? We ideally want this p-n junction to be forward biased, okay? And this one to be reverse biased. The reason for this will become clear, but we saw that in a p-n junction, minority carriers are swept across when there's forward biased. And it's reverse biased, you're going to keep the same charges, that's your concentration. So what's going to happen here is this is going to be forward biased, this junction, okay? Which means we're going to get a lot of electrons from here, because this N plus has a lot of electrons, right? A lot of electrons here are going to be swept into this P region, just like over there, and some holes from here are going to be swept here. That makes sense so far? Okay. One thing to note is that we're going to get a lot more electrons going from here to here than holes from here to here. And this is what we want. We want electrons to be the main source of movement. The reason being is if we try to satisfy both, we're going to have diffusion in 2 different directions. Current's going to cancel out. So we pick one carrier, our electrons, to be the main source of current. So we want electrons to go from here to here. Great. We want this one to be reverse biased. So this means we want to continue having electrons going up this way. But we don't want any to go down this way. We don't want any to go in the opposite direction to cancel out all the work we did over here. So what happens is we have our base voltage, VB. We have certain emitter voltage, VE, and certain collector voltage, VC. Okay? So now we want to bias this so that this junction is forward biased. So this means VBE. We want this to be greater than, well, let's just say 0 for now. It's not actually 0, it's around 0.6, because your diode has a certain voltage needs to turn on, that V phi over there. Let's say 0 for now. Similarly, we want VCB, right? We want this to be greater than 0 so that our collector is higher than our base. So this is off, right? So that's the first look at BJTs. And the idea is we operate in a certain regime based on these rules. And these are rules that we have to always follow, okay? If we don't follow these rules, we lose the electrical properties of BJT. It no longer works as we intended to, okay? So we have we have electrons going over here, push all the way up here to our collector. Hence the name collector. Collects the electrons. This emits the electrons. We have some holes going this way, okay? But these holes end up recombining with some electrons here. And if you're not familiar with recombination, that's fine. But what happens is these holes kind of disappear, and that's bad. We want to kind of always have a supply of holes, so our concentrations are the same at all times, so our device continues to operate. That's what this IB does. It supplies positive charge here. Okay? The details aren't super important, but that's the reason why we have a certain IB that we supply to our device that can maintain this equilibrium in a way. Okay? So what kind of happens here? I'm just going to write down a few equations, and then we can talk about it. Okay? So this is what our device looks like. This is a circuit model for it. Okay, so we have our base, collector, emitter. Okay, we have a certain IB, base current, collector current, emitter current. And generally speaking, if we follow all these rules, in this case we want this to be 0.6, and we want this to be, let's say around 0.3, right? We follow these rules, we're going to have a certain relationship between these three currents, okay? So one way you can think about this is that these are kind of, in series. Their currents are going to be roughly the same. We want them to be roughly the same, okay? So generally speaking, IC roughly equal to IE, roughly equal to beta IB, okay? This beta is the coefficient. It's usually around 100, 200. We designed for this. This is based off the physical characteristics of the BJT. Okay. Next thing we're going to talk about is, so we have this relationship between these three currents. We can derive an equation for IC, which is going to follow this relationship. Okay. So this is our relationship for IC versus VBE. Okay. So BE, remember, is this voltage from here to here. Ideally, this is grounded. So VBE is just whatever voltage we apply at the base. Okay. So a few things to note from this is if we apply a large enough VBE, we get a large IC. That's great. If this is small, this is going to subtract, and we're left with IS, which is 10 to negative 15. Super small. So we still have our rectifying behavior, which is great. If we apply a certain voltage, it's going to turn on a lot of current. Okay? So that's great. Any questions on that? Anyone? Can I erase this? Okay, cool. Okay, so there's a few things we have to be mindful of now. We have some equations there, which is great. It tells us how the device works. But let's now try plotting it out. Yeah, I'll use, let me try green. Green might be a bit better. Is that better?
Yes.
Yeah. Okay, so I'm gonna draw a few curves. Don't worry about exactly what they are just yet. Let's get into that. Okay. Okay. Cool. Let's continue using green then, right? Okay. Cool. So, a few things gonna happen here. We have dependence between IC and VCE. ideally, again, remember, we only want one way of controlling our transistor. We want to only modify VB. We change the base voltage, we get certain current. We don't want the collector, voltage to affect this. We set the collector voltage, we tweak VBE, and that's it. So we don't want to be in a region where if we change VCE, we're going to move from here to here. We want to be somewhere over here, where if VCE changes, hey, our current stays the same, right? So this is what we call our, forward active region, okay? This refers to, the junctions here, being forward biased, reverse biased, okay? And we have different levels of current here. So what happens is, we need a certain VBE to turn the device on. So it's around 0.6, okay? So if this VBE here is, let's say, 0.2, a really small current, that's not good, right? We don't want that. So once you get to around 0.6, you see this curve's now higher, right? So as the VBE gets even higher, our IC is going to grow, okay? Everyone kind of follow that? Okay. So this is great. This is our forward active region, but now we see that if our VBE is too low, our device isn't really on. It's just kind of there. There's a bit of current, not too much. That's what we call cutoff. The device is effectively just off, okay? Over here is what we call saturation. And what this refers to is, our diode here, this is forward biased. That's great. We don't have enough voltage here to really do anything with it though. So, we have enough voltage. We're at 0.6, that's perfect. But VCE is too small. So we still have changes here. Okay, that's where we're to saturation. This is in contrast to the MOSFET where saturation's good, BJTs, saturation's bad. We want to be here in our linear regime, forward active regime. Okay? So that's great. Next one we're going to talk about is how can we represent this guy in all its physics in terms of, circuit elements we've seen before. Okay? Go back over here for this. Everyone good with this? Can I erase it? I think we can do a break in like 5 minutes or so. All right. Okay, so here's our forward bias diode, our VBE diode. And then here we have what we call, it's going to be a voltage dependent current source. Okay, so what this means is we turn this on, we're probably here. But then we need a certain amount of voltage here for this voltage dependent current source to go from here to here. So that's how it's kind of modeled. Okay. So this is our just general diode that we've seen before. And this guy, let's put this up. We have this guy here, this current here. Right? And then this is an out current IC. Right? And these add together to create IE. Okay. All good with that? Okay. DC currents add up. and this is what we call our large signal model. And what this means is effectively characterizes this device across any voltages we would like to apply. This is what we look at, okay? There's a diode between the base and emitter, and there's a voltage-dependent current source between collector and emitter. Okay. And I guess next thing we're gonna talk about is what do we do to get gain out of our device? We've kind of covered already how, hey, we apply a certain voltage, we can change what current we have. That's the general idea of a transistor, right? A transistor. Now, how do we get gain out of it? How do we amplify something? This is where we want to now kind of explore, going back to our PN junction, the idea of a small signal model. Okay, who here has seen like a small signal model before, or like heard of transconductance? Okay, good. So I'm guessing a lot of 115A people. Okay, so what happens here is, let's say we are at 0.6. Okay, for our VBE, and this is going to go. So we're somewhere here. Okay, we have a certain current as a result. It's going to be IC. Okay. So we have a certain current resulting of certain VBE. What's going to happen now is, let's say we have very small deviations in our base voltage. Something like this. Okay. So you can kind of think of this like, if we were to plot this in time, VBE here. And we apply some sort of sinusoid across it that varies its voltage just a little bit up and down. Nothing crazy, super tiny amount. But because we're dealing with nonlinear devices, this small change here can take us from here, maybe over here, all right? It's quite a big change. Small little change here, bigger change here. So we see something that looks like this in our output current. Okay, everyone kind of follow? But we kind of notice how, although yes, it's a big change, we can formulate a way of, based on where we are, how much of a change do we get if we apply a little ripple? This is what we refer to as transconductance. And for those of you who've seen a small signal model before, this is going to be kind of familiar, because what happens is we've picked this point here as our bias. This is not working. Great. Okay. We've picked this point as our bias. We want to stay here. We want to operate somewhat close to it, and we want to figure out what current do we get. Okay. So what we do, we take a look at this slope here. Okay. What this slope tells us is, hey, if we kind of go from here to here, how much is our IC change, right? It's the meaning of the slope. Small deviations in our VBE give us certain deviations in our IC, right? So, how do we characterize this? This is our slope, right? Right? And this is what we refer to as our transconductance, or GM. So what this means is, if we have, okay, let's say a certain change in voltage, we want to figure out the change of current, right? Fairly simple equation for this. We have change in voltage, and we multiply this by our GM. We're going to get a certain change in our collector current, right? So now the general idea is, we pick an operating point. We pick a point where our BJT is on, is in the forward active region, and now we say, hey, let's apply a certain sinusoid to it. The reason why is because, well, in rap, we deal a lot with frequency. We want to apply sinusoids to them. We want to amplify them, send them to an antenna, send them out into space, receive them. So this is very useful, because now it's like, hey, if we apply a sinusoid to the input of our amplifier, what happens to it? Same idea here. So now we have a certain notion of gain. We apply a certain voltage, certain IC, and this gets converted through this factor called transconductance. So I think now we can take a quick break. Few of you look a little sleepy. I know for Thursday it's a little late. If any questions about what was just covered, feel free
Yeah.
to come up to me. Look like rejoin in 5 minutes or so.
Yeah, like